Excellent. So
you try to move the lights. I think it might just be the amount of sun coming off the snow over there.
There is no light.
No, it's up the front. It's over there.
Oh, yeah.
Thank you.
is it better?
Yeah, a bit better, yes.
Okay. So if you could bring the paper, that would be good. So what we will do is Magnus will help me. So he will show you what I see on the screen, and then for the Hangout people who are on the other side, they will see what I see on my screen. So I only can do one thing at a time. So it will be easier if I'm doing that for them and he's doing that for you. And you can open the article on your laptops anyway. So we agreed yesterday for a deadline for Friday for you to send me articles for your topics. And for those people who haven't done that, I encourage you to be quick to do it before Friday. And then for Tuesday, make sure that you send me the topics if you're not on the right-hand side column for the reviewing. And then we will do the big matrix, and then we will start doing things. I have to set up the Confluence page, so I haven't done that yet. So those of you who do have Confluence accounts, please email me your account name. And those of you who don't, then don't email me. And then for everybody else, I will use your HIG account to invite you, and then you can set up your profile and use email address that you want to use. Do you have any questions about the process? One extra note. I had a question from one of the students. So when you will be presenting your topic in serious games, and by the way, the papers for serious games were posted. So Simon posted the new papers for tomorrow for serious games. So in serious games, you read the paper and then you present the paper. So you say, oh, in the paper about the Parkinson tremor, Nowostavsky did this and that, and they made those claims, and so on and so forth, right? So you sort of present somebody else's work. In this course, you do a presentation of your own write-up. So you make a presentation on what you think is true based on the evidence that you got from the paper. So you have to say, I envision that this is true, or I believe that this is true because of the evidence from the paper. So you present your position. You don't present the position of the author of the paper. You present your position based on the evidence that you have from the paper or papers that you've used as a source. So it's a slight difference, right? So it's a little bit harder because here you have to take your own stand. And then you will be counter-argued by other people that your stand was wrong because there is an evidence suggesting that attention and distraction actually doesn't have influence on the tremor and whatever, if you can find some evidence like that, right? So you have to make your kind of your own point and then be possibly counter-argued by somebody else that your point was wrong. And, you know, in scientific discourse, we continue doing that. So we say, no, your counter-argument is wrong because we have evidence that your argument was wrong and so on, right? And we kind of keep doing that. In this course, we just do 2 steps and we stop. So we will not counter the counter-arguments. And we will also not review the counter-arguments. So the counter-arguments can be weak or can be unjustified, but you need to make as good effort as you can. So there was a question yesterday, what can I do if the original article is so strong that I cannot find any counter-arguments? Then, well, you try your best, and if you really can't, then you will make kind of an argument why the article is strong. So you, instead of counter-arguing, you will actually argue again for the paper and why it's so good, right? Why the arguments are sort of strong. So you can do it this way. And for the reviews, you just need to follow the logic. So you need to say, okay, the claims in this essay are sort of weak because the evidence is unjustified or because it doesn't logically follow from the evidence, right? So if I have a paper, like yesterday we had a paper about the tremor, and then if I make a claim that it is possible to distinguish between the different tremor types based on that article, you may say, actually, that doesn't follow. The paper was not making that claim. The paper was actually about something else. It was about distraction and attention. And you're now making the claim about the tremor in general, so you're generalizing. So you may point out some logical fallacies or logical weaknesses in somebody else's essay if they kind of make the kind of logical conclusions incorrectly. If they make the conclusions correctly, you just say, yeah, that kind of is correct, and they build the case correctly, right? So your review can be positive or negative or objective. It's up to you how you read the piece, how you read the short essay. And I had a discussion with Håkon, like what to write. It needs to be a short essay. The structure is up to you. You can write it as a single block of text. You can divide it into some small sections, but don't use headings. So it should be without headings, like subtitles of the essay. It should be just a continuous flow of text, but you can split it into sections. And you can use bullet points, you can use table, you can use whatever feel like appropriate for the argument that you're making. So it's a little bit up to you. And you have to think of a position that you need to take, right? So you have to have a position that you're taking. So you're saying something. You're saying distraction and attention is a good differentiator between the tremor, and here is the evidence based on this work that other researchers did. But that's my position. So you have to have a position that you need to defend at some point, right? So in the serious games, you don't do that. You just present the arguments of the papers, and we also discuss a little bit the technicalities of the papers, like we did yesterday. So we may say something about the structure of the paper, or you may say something about the logical flow of the paper, or you may say the paper was hard to understand, was too technical, and whatever. So we have different examples. We have some examples, as I was saying yesterday, of papers which are kind of not good. We had that last year. One paper was quite good, and one wasn't that good, was sort of a bit weak. So you may point some things like that about the technicalities of the paper itself in the serious games course. How many of you are taking serious games as well? Yeah, so it's kind of a big overlapping set. All right, so today we discussing repeatability, reproducibility, and rigor. Who read the paper? So what can you tell me about the structure of the paper? Did you like it? Was it easy to follow? Was it engaging? Was it clear what the paper is about? Was it communicating the ideas clearly? Yes?
I think it was fun, but in the beginning, it sort of felt a bit too vague for me, at least.
A bit chatty?
Yeah.
Yeah.
And I also felt that they were ranting too much instead of trying to be objective. And I sort of felt that I was rather reading a blog article rather than a scientific paper in the end.
That's probably correct. I had similar feelings when reading this paper. Any other comments? Is it bad or is it good? What do you think? To be a bit chatty or a bit like bloggy in a paper?
Depends on what you want to do, because this kind of text is reading more easily than just read paper.
Yes.
But then it's hard to use it like for real. Like it's hard to cite it or I don't know, use it as a real source of some information.
Mm-hmm.
It's just like recommendations, I would say.
Mm-hmm.
So it's easier to read it, but harder to use.
So why it's harder to use?
Because it's more subjective, I think, something like that. And it doesn't tell like it's less concrete.
Mm-hmm. Yep. So because they sort of they've done some research, they have some evidence because they're bringing up some other people's work suggesting certain things which they say are true, but they package it in a form which is more discourse-like. It's kind of difficult to distill exactly what their sources are and distinguish between what they think is true and what they have evidence for, which is true, right? So this paper has this sort of a bit of a flaw that some of the claims they make feel like they are correct, but they are not backed up by strong evidence. They didn't collect that evidence and presented it. They just presented sort of recommendations based on bits and pieces of research that they've done.
So they didn't follow their own recommendations.
Yeah, in a sense, I would say it's a little bit like that, yes. So they present certain recommendations for being rigorous and being repeatable and so on. And if you try to apply it to this paper, it kind of fails on some of the accounts. Yeah, yeah, that's a good catch. So I thought kind of this is exactly what I felt as well when I read it. All right, so about the abstract. So do you get exactly what they did just reading the abstract? Did you kind of understood exactly what that research was about and what the results of the paper were about just from the abstract, or was the abstract a little bit more introducing the topic, not presenting the actual ideas? Do you feel it's a weakness? Could the abstract be improved to kind of give you more insights of what exactly is in the paper?
Yeah, that's true. It wasn't clear.
No.
Abstract, what was the paper about?
Yeah.
You had to continue.
You have to continue reading. Yes, you couldn't get exactly.
Yeah.
Is the paper really relevant to you? You couldn't answer that question just by reading the abstract. So personally, I feel it's a bit of a weak spot. So abstract should answer the question: is this paper relevant to me? And just by reading an abstract, you should be able to answer that question. If from this abstract it wasn't clear, it was yeah maybe, but not sure. And then they have, it's quite of interesting because if you look at it, the abstract is actually quite short. And then they have quite a longish quote, right? In here. So the abstract is quite short, and then there is quite a long quote. So what is the quote about?
The experiment is done once.
Yep.
You're not supposed to do it.
That's right. So you have two professors. One who is Feynman. Do you know this guy?
Yeah.
So who doesn't know him? So who he is?
He's a physicist.
He's a quite famous physics professor, and he's quite famous for teaching. So he has a series of lectures which became quite famous in the physics circles, and he's kind of like a guru, teaching very hard physics concepts to normal people. So he says, he presents this anecdote that suggests that another professor says repeating an experiment is waste of time because it's been already done, so why we should do it again? What is your opinion? What do you think? Who is right? Is Feynman right, trying to suggest that experiments need to be repeated, or is the other professor which says, well, it's been already done, so why would you repeat that?
How do you know if some people are not doing it?
Say that again?
How do you know if some people are not doing it yet? To confirm this.
Yeah?
To confirm the results.
Yeah.
And to see also if the experiment is valid or not. Like,
Yeah.
the validity of the research.
Confirm it.
Yes.
Or to see if it actually is repeatable by methods that are dictated by the research.
Yeah.
And there's also, in addition here, the biggest crime in science is to make up that. And You know, we keep talking to you guys about plagiarism. Plagiarism is a tiny thing, doesn't matter that much, right? Because plagiarizing just says you're repeating data that's valid. You're just not crediting people the way you should, right? And that's naughty. You make up data, and people make decisions based on that data, particularly in, you know, this drug is safe, people die, right? If you don't credit the person with finding out the drug's safe, the drug is still safe, right? So making up data is the biggest crime you can do in science, and and if you've made up made up data, then it's not repeatable. So by repeating it, you verify that that's not made up. So you're actually checking potential for that big problem, which is making shit up, right?
Yeah.
So we would rather you just say, oh yeah, no, we didn't find anything. I only had 4 people, rather than saying, well, I had 4 people. If I make up another 20 people, I'll have statistical significance. Right? We don't want you to do that. I don't just make up fake people. That's the big crime.
Yeah.
So yeah, and repeatability avoids that kind of potential for people who have made stuff up.
Exactly. And sometimes you have a sample of 20 people, but you have like 5 outliers. You remove them, and it looks nice with the remaining 15 people. If you try to reproduce it, well, it doesn't look that nice anymore, right? You actually see that there were lots of outliers, and maybe the trend is not there. Maybe it was just made up. So you may not completely made up everything from scratch, but you may kind of influence the results to the point that it looks nice, right? And then by repeating it, you confirm and you make sure that what you claim on top of what somebody else did is actually true, because you're basing your things on things that you actually yourself demonstrated to be correct, right? So there are multiple reasons to do that. One reason is that you verify somebody else's results. The other one, you actually reproduce the environment, and you make sure that now when you're doing this new thing, it kind of worked with the old thing as well, because you have no guarantee that if you had conditions, if somebody had conditions A, or in his case X, and achieved A, right? Then I actually have the same X conditions. Maybe I cannot reproduce those X conditions. Maybe I cannot achieve A if I reproduce the X conditions. So by redoing it, you kind of make sure that your setup kind of is the same. So here's the difference between reproduced results and repeated results. What's the difference if I reproduce something or if I repeat it?
You don't get the same results.
No, but what? Yeah. So there is the title is repeatability and reproducibility. What's the difference between those two terms? What does it mean I repeated something, and what does it mean I reproduced something?
You repeat the experiment and the methods that the paper used.
Yes.
But reproducing means reproducing the whole paper.
Almost. So the first one is true. So if somebody did the results like I did yesterday with the paper, you may say I want to repeat it. So you take a sample of people and you use exactly the same tools I used. You use exactly the same tests I've used. You measure the hand tremor and you try to repeat those experiments with different people, but the same method and the same tools and the same everything, right? So that's what repeatability is, that you are able to do that. So the paper should describe exactly how we did it, what tools we used, what methods we used, what parameters for the wavelet transforms we used, and you basically do the same. You collect the data and you use the same numerical analysis we did, and you should obtain the same results as we did, right? Reproducibility is you say, hey, there is this concept of attention and distraction influencing the tremor, right? You may use that now without using my method. You may come up with your own method. You may come up with your own tests for being distracted and being attentive to a task. And you try to reproduce the same effect with a different method, with a different methodology, with a different tools, with a different numerical methods. Because we had a set of experiments which suggested some larger truth. And now you say, I want to reproduce that truth. I want to make sure that this is actually true. So I will have my own set of tools and my own set of experiments to confirm that, to reproduce that truth, right? So you may use different methodology, you can use different tools, you may don't use mobile phones, you may use different tasks or whatever, and you try to reproduce that effect. And then if you did reproduce that effect, you reproduced that larger truth. And now we have two evidences, right? We not only verified that I did correct things and the experiments are reproducible, repeatable, we also said that bigger truth is reproducible. We can use different methods to achieve the same effect. So this is kind of slightly different. And in the paper, they make the case later on, if you scroll somewhere towards the end. In section 4.4, reproducibility, they say independent confirmation of a scientific hypothesis through reproduction by an independent researcher is at the core of scientific method. So that's what science is about. So science is about coming up with some sort of general truth about the reality and independent researchers confirming those truths independently of each other. So repeatability is one thing, but reproducibility is much stronger. Because I can have an experiment which is repeatable and it demonstrates something, and I can repeat it multiple times. It doesn't mean that larger truth is true, because people may not be able to reproduce it. So if I just change things, people may not achieve that effect, right? So maybe there is something inherent in our experiments which made the distinction between attention and distraction causing certain effects, and you cannot reproduce it, right? So if you cannot reproduce it, that means that larger truth that we claimed from those experiments may not be true, right? We believe it's true and we believe it's reproducible, but we don't have a second evidence. And now independent researchers can do that and kind of confirm it. So that's what the scientific method is about, and that's what reproducibility is about. All right, so those are the kind of the core kind of concepts in this paper, and it's hard not to disagree with that. It's sort of fundamental into the scientific method. So let's dive a little bit into the details of what the paper is about. So if we go back to section second page, the beginning of the second page, and we have some claims. They basically say we have applications with unrepeatable results, unreproducible results. We often measure the wrong thing, or we measure the correct thing, but in a way that is useless, right? And they kind of do this statement without going into details, and then later on in section 3, in case studies, they try to bring some cases which demonstrate that, right? If you are very thorough about making those claims, you would have to provide evidence. You would have to say, we have analyzed 300 scientific articles from 2015, and then 96% of them had unrepeatable results, because to repeat them, there was kind of some information missing in the paper, so they were rendered unrepeatable, and so on. You have to be quite thorough. And there are some review papers which go into that level of details. They tell you exactly what search queries they've used to kind of facilitate, elicit the papers. They tell you exactly how they made the selection, what papers they've used, and they provide you kind of statistical details of the nature of the papers, and then they make the claims like most papers have unrepeatable experiments, that people cannot repeat them because they don't tell exactly how to do that, right? And that's probably true. Like if you think about it, and if you read papers, you may say, yeah, that's probably true, but scientific method is not about, guessing. It's about hard evidence. So it's kind of it's hard not to disagree with what they say, but we don't have evidence for or against, right? So we believe what they say is true, but you have to have some stronger evidence, and you should be more thorough if you're doing reviews like that. So how you can make your experiments repeatable. So when you're making your own experiments, what do you need to think of or think about to make them repeatable by other people?
Just describe carefully and in greater detail all the methods you've used, all the tools and the experimental setups, and
Yeah.
so that so the other researchers can just follow all those methods and tools and achieve the same result.
Yeah. What else? What else you have to think of?
To state in the paper, or
Yeah.
just like
To state in the paper and in general, like when you're thinking about your methods, or so you have some sort of a research topic for your master thesis and you kind of setting up some experiments, and then what you have to take into account, into consideration.
Well, I guess we kind of have to think about the actual methods, or the things that we do are actually repeatable, not to make something that nobody else can repeat. Even though, like, if we make something only for one time, and even if we describe it, if it's not really repeatable, then they cannot redo it again.
Yeah.
also taking into consideration the things that might change in time.
Like what? Some examples.
I don't know. In last semester, we had like a scientific paper for like laptop or mobile use something in class, and they had a research about that. And it's kind of from 2011, I think. I'm not sure, but that changes. So students really use more laptops and mobile phones in class. So
yeah,
that's not repeatable.
Yeah, that's right. So you have to kind of really carefully think about everything that contributes to the experiment and contributes to the results. And often it leads to difficulties. So for example, when you, let's take our study, okay? So in our study, we have used wavelets and support vector machines for the clustering and classification, okay? And a lot of students, they take MATLAB and they use a toolbox in MATLAB to do the calculations for them. So they have certain data set, they use a MATLAB plugin, they feed that data set into a MATLAB plugin, and it spits certain clusters or some results, right? And that's fine. But then a year later, somebody wants to repeat it, and they take the same data set, they feed it into the same plugin, and they get different results. Why? Because the plugin was updated. It's not exactly the same thing anymore, right? So how can I do this? How can I repeat or make sure that the results are repeatable if the software is changing, right? Well, we didn't use MATLAB. We wrote everything ourselves, right? So we used libraries, we used parameters that we knew, we kind of researched the parameters that we have to use, and then we describe those parameters. So then if somebody from 5 years from now wants to do this, they can do exactly the same thing. Sometimes there are updates which don't change the version number. You may say, well, what if you just said, we were using a plugin version, blah, 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 and then somebody else can use the same version number. Well, it actually happens that some security updates sometimes happen without version bumps, right? It should never happen, but it does happen in software. And big companies do that. Like Adobe was quite famous for that, and other big companies do that. So they have sort of updates which say, yeah, it's still version 1.5. It's just an updated version 1.5, right? So if you said in your paper that you use version 1.5, well, it may not matter. We had that with some microsystems too. We were depending on, in one of our projects, we were relying on a particular firmware version so Sun was producing hardware. They were producing Blade servers, and we were getting them with a particular firmware on those blades. And it turned out that the firmware version numbers kind of sometimes stayed the same, even though everything else changed. So we were kind of relying on the version number to tell us that our software will correctly run, but it turned out not to be a reliable predictor, that sometimes it wasn't running correctly because the firmware version seemed to be the same, but it was actually already updated if it was shipped later. They especially do that for experimental development. So we were using the hardware which was not sold yet, and then the versions were really unreliable. For the production systems, I think they're more careful, but still, you cannot really trust it.
Yeah,
So
my friend who was working in Australia for Vision and Fire with like 1,600 developers. He was the software configuration manager, and they were using Rational products, and IBM bought them. And then they had a problem, and he went through and he tracked down and found the build numbers, and the build numbers are identical, and then checked the file sizes, and they were different.
Yeah.
And he said,
how could that happen?
this is the Rational product designed to do software configuration management, and they're changing them without managing their software.
Yeah. So you.
Yeah, that's great.
It gets complicated, especially if you're doing research with wearable technologies and so on. So, for example, if you have a smartwatch and it measures your heart rate, which we do, and you have some sort of experiments which continuously pulls data from the device and uses it, right? There were studies like that. So there was a study of a person tracking his stress levels, and he was using a wristwatch which was continuously pulling his heart rate and his skin resistance by how much he was sweating, and he was logging independently meetings and what activities he was doing, right? So he noticed that when he is in lectures and giving presentations, he's a bit more stressed, and then when he's at home, he's more relaxed. And it was kind of going okay, right? So he had some log data and some biometric data from the device. And then at some point, he got really stressed, right? Suddenly, like it was kind of everything went up. And he was like, for a couple of months, he was puzzled. Like he was tracking to see what happened, and he tried to relax himself and so on. But what actually happened on that date, there was a firmware update on the device, right? And suddenly it was much more sensitive, and it was kind of giving more precise readings, and suddenly everything kind of changed for his analysis. And it was kind of unexpected because they don't keep track. Like you just do automatic update of the software, and suddenly things are completely different, right? So then he started like noting when certain version updates of his software on his mobile phone and on the wristband happen, so he can track that as well and treat it as an independent variable, right? So, but for someone who wants to reproduce or repeat, for reproduction it's okay, but for repeatability, if someone wants to repeat some of his experiments, it's actually impossible to go back to those firmware versions which are historical. You can get a wristwatch and it will have the current version, and you cannot flash it back to the 2 years ago version he was using. So you will, by definition, not be able to repeat his experiments, right? Unless you're using some upper firmware and using some devices which you can reflash yourself and kind of ship the software so people can repeat it, and you have to kind of plan it and think about it. You have to sometimes really carefully think of the whole pipeline that happens from the moment you start collecting the data, and then what will happen with the data, to the moment you have your graphs, how other people can repeat it. There are two more stories. When I was doing my PhD, I was very skeptical about everybody cheating in their scientific papers, right? So I didn't trust anybody. So I had to repeat everything I was using for my own studies, so I can, first of all, verify that what they got is correct. Second, I can see all the details which are not in the papers, like the outliers and so on. So I see all the mechanics of what actually happens with the data and how it looks like, because the results are always very generalizable or generalized, and then the details are kind of missing often. So I wanted to see the details. And third, I wanted to have a kind of a setup that allows me to say, I've done some changes to somebody else's work and I got those results, as with the quote here. I wanted to do that. And one of the kind of a cornerstones for the work I was doing was done in middle of 80s, and it was done in Chile by two Chilean professors, actually a professor and a doctoral student. And they publish a paper and they provide a setup for experiments which they've used for. I was doing work in the sort of artificial life situation. So you have sort of like an automata setup in a computer. You have some rules, and then you see certain things evolving based on those rules, right? So I tried to reproduce it, or actually repeat exactly the same as they did, and I kind of it was not going too well. So I did kind of a lot of literature search, and I found a guy in UK who was also repeating the experiments from 80s. And I found his paper. And the paper was basically a story of how he repeated those other guys' results. I couldn't, but he managed to do it. And it turned out that when they originally published the paper, they forgot about one of the rules, right? And one of the rules was missing in the set of rules that you have to put in to reproduce the same or repeat the same effects. And he was trying to repeat it, and he was not getting those effects. So he contacted them, and they went back and forth. In the meantime, the professor died. So it was getting harder. It was getting very elusive to be able to repeat it. But fortunately, he contacted the younger professor, and they kind of back and forth, and they nailed down that actually one of the rules was missing. But it took 15 years, right? He was doing this experiment for 15 years. And then after 15 years, he managed to repeat it, right? And he said, yay, we have the proof. But the interesting thing is that now the original paper is still with the missing rule. And now the new guy's paper is the more valuable one because it contains the correct data for somebody else who wants to repeat it, right? But it wasn't a trivial story, and it took him a very long time. So I was really happy to find the other guy paper because it saved me, 15 years of digging and trying to repeat the original author's article. So it often is not trivial. It's often, little things that we forget to put in, which cause difficulties in somebody else's repeating it. Reproducing the effects is okay, but in that particular field, a slight variation in the rules makes it's kind of a very chaotic. So if you kind of misalign something a little bit, you get completely different results, and you cannot really compare it to the original paper. And my idea was that they were basically working with things which so if you have an organism which needs certain things to generate itself, right? So I have some material which is needed for this organism to sustain itself, right? So it kind of sustains itself by sucking those materials in, and it possibly has some byproducts, right? So if those byproducts are used by another organism which also sustains itself but has other byproducts, then you can have a cycle. You can have a stable system like in ecology where organisms sustain themselves because the byproduct of one organism is the input for another one, and then you have kind of a continuously stable ecosystem because everything is sort of balanced, right? So they were researching this, and they were researching the kind of mathematical properties of how it works, and whether it's possible to have a completely closed ecosystems like that, where you don't have anything coming from outside and anything coming out. Because normally we have stable ecology or ecosystems with the energy coming from the sun, right? But we don't give back to the sun, so it's sort of one-way street, something like that. And there are biological experiments. For example, you have like a glass ball which has a stable ecosystem inside, and all it needs is the sunlight, right? And it's a living glass ball with kind of an ecosystem inside, and all it needs is a sun energy. What we were doing, we were trying to think of the kind of a system where you have nothing coming from outside and nothing coming out, and kind of sustaining itself, and what are the properties of those kind of elements. So they did the original work on that, and I was kind of really interested in how it works and how it can be used in computer software for software to kind of produce itself, right, and sustain itself. So it was kind of interesting. And then Simon, yeah, he unfortunately he left, but he also had a good story for his PhD, where he basically, and you might have heard it, it was kind of done before the virtualization was sort of hot. He packaged up an entire Linux distribution with all the software that he used and all the experiments that he used. So then you can kind of, with a script, you can relaunch it and sort of repeat the experiments and the results that he was doing, right? So he kind of made it really easy for somebody who wants to repeat his experiments by packaging up all the detailed information about all the packages and all the Linux distribution dependencies that he needed for his, GNU plot and his LaTeX and his statistical packages, and what he used some neural network software and so on. So you kind of can basically have access to all of that. It was all open source, and it was kind of easily repeatable. And because he automated it and he scripted it, it was really easy for him to repeat things as well. So if he needs to redraw some of the graphs, or if he got 20 more people into his experiments, he could just run through the whole pipeline and kind of repeat exactly the same chain of dependencies. So it's not trivial, but it is quite important to think about it. All right, so let's have a short break. It's 11 o'clock, so let's have 10 minutes break. And after that, we will talk a little bit about the case studies that they've done in the paper, and we will talk a little bit about statistics and a little bit about computer hardware. Because part of the paper, which I quite like, is it is kind of a little bit geeky in places. So they talk, for example, about memory placement when you do any sort of testing, right? And they talk about this kind of being skewed to the right side. And those are kind of very interesting concepts that you, as computer scientists, you need to sort of appreciate a little bit. And they might not be completely intuitive, but they're sort of fundamental of how computers work. So yeah, so let's have a short break, and then we will talk about it after. So 10 past 11. All right, so let's continue the discussion on the paper. I will share the screen. All right, so let's make a simple simple case study. So you measuring something that runs on a computer. I don't know. You have some sort of algorithm for augmented reality, perhaps. You're trying to do some vision processing, and you have a mobile phone, and you say, will it work in real time, right? So you need a certain frame rate. Let's say you're doing 30 frames per second, and you're asking a question: will this algorithm for detecting some features in the scene be sufficiently fast that we can use it for real-time applications for augmented reality? So how would you set up experiments confirming that your algorithm is fast enough to do it in real time? How would you do that?
You mean that we have specified hardware that we use?
Yep. So we say, okay, we specify the particular hardware. We use this kind of, we use Nexus S hardware. We say, okay, this is the RAM it has, this is the CPU it has, this is the firmware version, operating system. We cover all of that. So in that context, is repeatable. What else do you need to take into account?
What software is running next to it?
Exactly. And how can you take care of that? You really can't, right? The users will be out there doing whatever they're doing with the phone. There will be some background apps running, and you have no way of knowing what they will be running when it happens to run this augmented reality thing, right? So how you compensate for that?
Maybe you have to vary like load of mobile phone.
Exactly. So one way of countering it is that you have to generate circumstances which you can say are modeling the real world behavior, right? So you may say we have maybe 3 classes of users, the ones which have no background apps running, so it's like a best case scenario. Then we have some evidence that on average, if you kind of randomly check, how many background apps you have currently on. You say, okay, I have, I don't know, I can check how many I have. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we do a poll, and the average size is, I don't know, 10. We say, okay, we model kind of a moderate users who have about 10 background apps. And then we kind of model a heavy use, maybe 50 or 100, right? Kind of really heavily used phone. And then we sample across those boundaries. You can randomize things, right? So you may say, well, instead of doing those 3 classes, we just have a distribution. So we will have no load at all. So just clean phone. And then we have a very heavily used phone, 100% utilized, I don't know, with some background processes chewing up the CPU and chewing up the RAM. And then we will kind of use either a kind of a normal distribution, or we can use a straight line. And every experiment we do, we just sample and we just generate the load according to the distribution that we want. We kind of randomize the loads and collect the data this way. Okay, so let's say the experiments we are only interested in the best case scenario. We don't care about the variability here. We say, no, we kind of disregard that for now. We just want to see if this algorithm works in the best case scenario, because if it's too slow for the best case scenario, then it's too slow, right? And if it's good enough for the best case, then we can do the other studies to see how it actually will behave. So we say, okay, let's do the best case scenario. And we're using Android platform. So we're using the Dalvik VM that's there. And then we're trying to model that. So what else comes here that we have to think about? They talk about it in the paper. So where these guys are from? What field of research they mostly do?
In Java, and they talk about garbage collector.
Garbage collection, exactly. So, you know, when you're doing this, when the garbage collector kicks in, everything slows down because they kind of occupy your CPU cycles and they do memory access and so on to clean the garbage from the memory. So one strong effect that you have here is the effect garbage collector has on your results, right? So how would you deal with that?
But should you deal with it? Because it will be there in the real world.
That's right.
Yes.
So
That's right.
Accept its existence.
So you know it will be there when the users will run it. That's correct. You cannot really eliminate it completely. In terms of repeatability, you know, so if you do one measurement, you run it, right? And let's say we have the, so this is how long it took. You did one experiment and it took that long, right? So then what can you say? Can you say, well, it will take about T1? Or you cannot say that yet?
You have to repeat it.
There is certain uncertainty. We don't know what is the error, like how much, you know, variation you have here, right? We don't know that. You know, part of the variation is caused by garbage collector, right? So
you have to repeat a lot of times.
You have to repeat it, right? So you repeat the measurements, and then you get, you know, you get kind of a cloud around T1 somehow, right? So if we take all the measurements and we order them here, so and measurements, then we will have kind of a certain distribution, and then if we count how many points were at T, you know, at T0 around here, how many points were there and how many points were up there, it should come out with some sort of a normal distribution around the point. So if this is count, so we're counting points, and here is our T, right? So T0 to Tn, and we're counting how many were really fast and how many were really slow. Then we will have some sort of histogram here. So the shape, if the shape looks like that, you can hypothesize, okay, the mean time is around here, right? Because sometimes it goes slower, sometimes it goes faster. However, in the case of measuring time on computer, we were just discussing it before the break, you will have it very, very heavily skewed towards the right. So the curve actually will look more like that. Why? So why ideal curve looks like that, and why the real one looks like that?
Because it was biased by something. Probably.
So you have to think about it. So if I'm running something, and let's say it should take, so this is the average time it takes it, right? So the average time is here. Occasionally, it will be, the optimal conditions will happen. The memory allocations will be kind of aligned perfectly, the garbage collector will not kick in, and we will run perfect run, right? So occasionally, we'll run a perfect run. So the number of perfect runs here is occasionally, right? And then occasionally, I will have longish runs, right? But very rarely, but will happen, I'll have very long runs, right? Somebody may call, or the memory is so fragmented that the garbage collector has to kick in 1,000 times. So occasionally, very few times, I will have very long time. And that skews everything to the right, right? So those two are kind of the same, but occasionally I will have very, very long time. And I will never have occasionally like instant, like, whoa, yeah, it just happened, right? So this will be empty. I never have things which happens instantaneously, right? But I do have things which take ages, right? Sometimes you have that. You know, you type in your password and sometimes your computer takes like mega longer than usual, right? It happens very rarely, but it does happen. It's like, oh, come on, right? So that's why this curve is skewed to the right. So how you counter that? So if we assume normality, obviously this is not normal, right? So what they say in the paper is, well, you know, assumptions of normality is always better than nothing, right? So if you assume nothing, you just make your measurement and then report it that's bad, right? If you make your measurements, assume normality and calculated the mean from the data, that's better than doing nothing. But in fact, you should kind of count this this effect in as well. So what tend to happen when you're measuring time is we tend to disregard it and we tend to pick the best runs only, right? So we say it's kind of hard to say what will be the average time, but we can tell you what's the best time because that's the fastest we ever got. So you run your experiments 1,000 times, you got one which was blind, you know, the fastest, and that's your best case scenario. You know it will never or very unlikely run faster than that. That's your best case. If the best case is too slow, you know you're too slow, right? No matter what. So we often do that. We actually run multiple times, not to calculate statistics, but to calculate what is the actual possible fastest run. And then we say we have evidence suggesting that it can run at least as fast as this in perfect conditions, right? Other than that, you have to calculate some statistics. So what can you calculate? What's the basic statistics that we calculate? So we did, I don't know, 20 runs, you achieve different results, and then what do you do? Yeah, you calculate the mean and
distribution
and the
Standard deviation.
yeah, exactly. So you calculate the variance, and from variance you calculate standard deviation, right? So you know what is the variance in the data and what is the, you know, what is the error bar around. So what were the 95% of data fitting in. Usually we take 95%. So we say, you know, that's the average, and then between those 2 points, we had 95% of points. There were 5 points which were lower than that or higher than that, but 95% of data was between those 2 points, right? This is important because if you have, right, so let's say, this is bad. Let's say I have guys reporting some result, and they said, we achieved that, right? And I ran some improved algorithm, and I said, well, I achieved this. I'm beating the guys, right? I'm the better one, right? My average is higher than their average. Which algorithm is better? Well, it depends, right? It depends. If the algorithm variance is like this, and my algorithm variance is like that, right? I cannot claim anything. I actually cannot claim anything. I don't know if I'm better than them or not, right? Why? Because this difference between my result and their result is completely insignificant compared to my variance, right? That's meaningless result. And you often see that people report the results without the bars, and they say, oh, look, I'm better. Look, by this much, I'm better, right? But you don't know, actually. Without the variance from the data, you cannot really tell.
You can say it's unreliable.
Yes. So if the if this variance is very small, and if this variance is very small, then we may say maybe I'm better, but I still cannot tell from this particular graph. I would have to do, analysis of variance, for example. I would have to do additional statistical test to see if indeed this variance with my result is significantly bigger than the variance and the result they got. And then this test would tell you if that's correct, right? If you actually have statistically meaningful difference. Because if I run that and the result says no, you don't have statistically significant difference, then I cannot tell, right? Sometimes you can do this if the results are actually quite significantly apart. You can just do the, the t-test and say, yeah, this is better result than this. But if they're kind of close enough, you have to run additional statistics. So for your master thesis, most likely you're gonna run just standard mean and standard deviation, and maybe t-test, and maybe this one, right? So those are very simple tools statistically that you can run on your data to kind of tell whether you have statistically significant results. If you don't get statistically significant results, then what?
You prove the null hypothesis.
Yeah. So you say, well, there is no difference, right? I had a student who was doing, he was developing a new desktop setup. So we had, yeah, so maybe I switch to the camera. Yep. So for the people who are watching there, right. So I had a student who was developing a new desktop environment. So normally you have on the mobile devices. So normally you have a very limited amount of space here. So what Twitter and Facebook are doing for your feeds, they kind of divide the screen into panels. So you can swipe right or left, and you have kind of a bigger screen. So you have a two-dimensional, you can imagine it as a two-dimensional desktop in front of you, which you can go left or right, right? And you can sort of have certain feeds arrange that. So we use the Twitter client for this, and he had some, trending topics, some friends things, and the general flow, and something else. So we had, I think, 4 different panels in front of you, and you can swipe left or right to see the information in the individual panel. And you have to find certain information. So you have to find when Alice wants to go with you to the cinema, when there is, what film there is in the cinema. You have to find the weather and so on. So you had certain tasks. We prepared those feeds, and you have to find those things, right? And you can arrange the feeds the way you like it. So you can have certain things swap, right? So you have a certain spatial relationship between the feeds. The other interface was that you don't swipe. You hold the phone, and it shows you a feed. But if you look towards your right, you're like inside a cube. So you have a cube around you, and you can watch the feed which is on the cube, right? So you can watch in front of you, there is one feed. If I look left, there is another one, and the right is another one, and behind me, actually behind, there was another one, and then we had a floor as a configuration panel, right? So you kind of inside the cube, and you can either configure stuff or look at the feed doing the thing. And we use a kind of a chair which you can rotate. So you can kind of easily rotate yourself around. The hypothesis was that swiping is kind of harder and longer, and then the spatial information being around you will give you better feel of where things are. So if you know all the weather stuff is on your right, you can easily get there, right? Because you know it's on your right, and then the friends' feeds are on the right or the left, whatever. So the hypothesis was that the cube metaphor will help you to do that. because there was some evidence that people, if you orienting yourself in three-dimensional space, you kind of remember locations of places. So you kind of remember locations in places better if it's in a 3D rather than on a flat map or on 2D map, right? So you can, like, if you don't know where north and south is, and I drop you on a two-dimensional map, and I say, now you kind of next to a church and tell me which direction you have to look to go to the Fjellhallen, on the two-dimensional map, it takes a while. But if I drop you in a kind of a three-dimensional environment, and I say, yeah, the church is towards the right, orient yourself where Fjellhallen is, you kind of have a better spatial memory of how to face Fjellhallen, knowing where the church is, right? So that was the hypothesis. Okay, we got students, we ran the experiments, he ran everything, he ran this, no significance. Well, is it bad or good? Well, we kind of failed, right? We thought we will build something better than what already was, but instead we built something which was the same. And it was kind of a good result, right? We say the well-developed interface, which, you know, a lot of designers put effort into, was not better than the interface a student did in 2 months' time using the cube, right? That his interface, even though was not polished, was not very well designed, performed as good as the well-designed 2D interface, right? So we said, yeah, well, maybe if the interface was really improved and kind of put more effort into, maybe it will be a better result, right? But we said, well, so far we confirmed the null hypothesis, that there was no difference. And that was kind of good, that it was not worse, right? It wasn't better, but it wasn't worse neither, right? It was kind of the same. And yeah, and he published the thesis, and we published a paper as well, you know, demonstrating that result, that it was not what we hoped for, but it was still a good result. So sometimes confirming a null hypothesis is okay. Right, so with the article, coming back to the article, there were a couple of things that they talked about beside the statistics, and they talked about memory placement. So what is it all about? Why memory allocation and memory placement matters? Yep.
It could affect performance, which then could affect the results.
Exactly. So why does it affect performance? Yep.
And random memory placement, which affects cache hits and so on and so forth.
Exactly. So everybody is aware of the caching kind of that happens on the modern computer architectures. You had it in the operating systems, or yeah. So it is. We normally don't think about it on kind of a daily basis, but when you're doing your experiments, and especially if you're measuring performance, or if you're doing anything to do with you know, performance metrics, those are little things that you have to take into account, right? So how important is it? It's super important. However, it depends on what scales do you do the measurements, right? So for example, we were, for the paper I discussed yesterday, it took about 20 minutes to run the clustering on the mobile phone at that time that we were using, right? So, you know, if you're running a computation which takes about 20 minutes, you're thinking, well, you know, memory placement and caching, yeah, important, but not very, very important. The killer was the garbage collector, right? Generating objects and disposing them and kind of going over the objects was the main contributor to the performance measurements. So depending on which scale you're talking about, you may or may not pay as much attention to the memory placement as in other cases. If you're doing anything with networking, or if you're doing anything with like real-time video processing, like we discussed with the augmented reality, then it's super important. We had a project with where we were optimizing the pipeline for packet processing. So you have a 10 gigabit network coming in, you have packets being streamed to your box, and then you have to pick the packets and kind of process them and decide, what to do with the packets. And you have to do it as fast as possible. And we had multiple cores to handle that. So we had, up to 128 cores to do the processing. So you not only have, so you have the cores to do parallel jobs, but you can also use the cores to do the pipeline, right? So I can, because with a single packet coming in, so if I have a generator, the packets come in, and then the packets are kind of coming in sequence, right? So I have now this processing unit, and of course I can say, okay, this packet kind of goes through this, next one goes through this, and next one goes through this. So I can do in parallel certain things, but there is a limit of how much makes sense to do in parallel. And we had more cores than it made sense to do in parallel, so we were using the cores to basically optimize it in such a way that the code which needs to do some processing resides in the L1 cache of that core, so that it never hits the cache miss when it starts processing. And that significantly speeds up what happens with that packet if it goes through the pipeline, if the code fits into a L1 cache. So you were trying to make your functions small enough that they fit in. If you added one extra line or an extra, loop, sometimes it went off, and then you have a lot of cache misses, because once the logic gets to that point, it needs to reflash the L1 cache, and then you have like, an order of magnitude slowing down there. So like L1 cache, let's say, is like 10 times slower than having things directly in the registers, and then L2 is like 100 times, and then L3 is 1,000 times, and then accessing something from RAM is just way too slow, right? You cannot really ask for anything from RAM because it just kills your performance completely. So you try to keep everything that is possible in those caches. And then also you want to share. So if you can share something in L2 cache between two cores, that's great, right? Because then it's not, you're only losing around 100 times the performance, not 1,000 times, right? So it's sort of important of where you place things and how you arrange your arrays and how you do the transfer of data between the cores. But that's kind of a really specific, a very close to metal sort of optimization techniques. Normally, on the scales that more applications operate, that is not as relevant. But for this guy's research, it was, because they were researching garbage collector, and in garbage collector terms, those metrics really matter. Yep.
I have another example of this when this cache matters.
Yeah.
It was in our university when we were making some experiments in parallel computation class, and we were taking experiments with different algorithms and measuring their performance.
Yeah.
If we will scale this algorithm on multiple cores, dual processors, and eventually we get, for example, it was algorithm that parallels perfectly, and we had 4 CPUs, and in the end we got increase of more than 4 times. It was like 4.1,
that's right.
For example.
Yes.
And teacher said us like it's theoretically impossible to get this performance.
Yeah.
And you made something wrong. We remake everything, check everything, and got the same result. And the reason was that for CPUs, each CPU has its cache.
Yes.
Because of that,
exactly,
we get this increase more than
4 times. Exactly. Yeah. So that's a very good example, because that's the example of like hyperparallelism. So normally, of course, if you have a task which takes time t, and now it's perfectly divisible, and then I distribute that to 4 cores, then the theoretical maximum I can get out of this is 1/4 of t, right? So if the task took like 4 seconds, now I can do all this in 1 second because I have 4 cores doing those things independently. But in fact, I can do it in less than 1 second because of the caches, because of the intrinsic benefits of having those caching hierarchy and those things being really close to the CPU being so much faster than everything else. So that is kind of interesting. And that effect needs to be taken into account when you're doing kind of optimization for multi-cores, or if you're investigating parallel algorithms and so on. Yeah, it's a good example. So what else did they talk about in the article? So they say, do the statistics, count for the execution time in a proper way, be aware of being skewed to the right, make everything possible to be repeated, and reproducibility is the highest possible goal that you should aim for. What else did you took out of the article?
That we should make clear abstracts.
Yes, that's a good one. Abstracts are important. We should make them count. What else?
Encourage reproduction studies.
Yep, they're encouraging reproduction and repeatability studies. Even repeating something is worthwhile. They spent towards the, like from section 4.5, that spent time on benchmarks. So why do we use benchmarks, and what are the weak points of benchmarks that they kind of used? So there are 2 types of benchmarks. You get the kind of a normal benchmarking, like I want to buy a new gaming GPU. I look on the web and I have some benchmarks which compare GPUs, and they say in this particular benchmark that GPU is faster than this one, so I'm gonna buy this one. Or you kind of smarter than that and you say I'm gonna plot the performance against the price, and I'm gonna find the sweet spot, which is the price to performance ratio, and I'm gonna buy that, right? Or you say no, the price doesn't matter, I just want the fastest, right? Well, does it matter for you how the benchmarks are done?
Wow.
Of course it matters.
Well, it depends. Because benchmarks, as I said, for example, it can be just one number.
Yes.
That shows the average everything, and that cannot suit you, for example, if you want something specific.
That's right. Yeah. So it depends what sort of person are you. So if you are a normal person, then having just one number at the end of the review is fine. You just say, I just want to compare those laptops or those cars, and this car comes out with like 10 stars, and that comes out with 7. Yeah, I'm gonna go with the 10 stars, right? You don't know the details. You trust that the benchmark took a lot of things into account, which covered a broad use cases or whatever, and then they pick the best, right? But if you're more research-centric, you want to say why this one is better than this one, where, when this one outperforms this one, and what maybe the weaker one has certain features that I actually really want. So you need to know details, and to know details, you have to, as they are saying, you need to actually, single number doesn't tell you that. The single number is insufficient. And then if you have benchmarks which have 100 numbers, it's kind of, you get lost. You cannot compare, 3 things, each of which has 100 things, and then like the matrix is, incomprehensible. So they were kind of recommending that benchmarks should go for a small number of things which are kind of representative of various properties of the thing that they are measured, but they shouldn't collapse it to a single number. It should be more multidimensional, but not overly complicated. And they said you have to be very clear of how the benchmark actually work, what they measure, right? And we need to know that. That's why some of the early benchmarks for Java were this, stopped being used because it was a proprietary software which source code was not available and nobody really knew exactly what the benchmarks are doing. They were measuring something, but you cannot really tell what they were measuring. So the benchmarks have to have some sort of a verbosity or transparency to them, that it's actually clear exactly how they work and what they measure. You could see that. You can see this tension with marketing. When the digital cameras started, I don't know whether you remember those times, but there was times without digital cameras, so only film was available, and then digital cameras happened, and suddenly the discussion about the quality of the cameras was reduced to a number of megapixels they had, right? The more megapixels you had represented the better camera you could have. We never had that discussion with the film cameras. We never had a quality of the camera reduced to a single number before. So the quality of the camera was a complex issue. It had to do with the color reproduction, with the clarity and sharpness of the image, with the spectrum of the shutter speeds, of whether you can take sport shots or not, and so on and so forth. It was a kind of a complex thing. So if you were to buy a camera, you have to be kind of discussing it with somebody to pick a right one for you, right? After that, suddenly it was a single number, and people were just buying the bigger number ones, right? It sort of stopped because now, whether you have 10 megapixels or 40 megapixels kind of doesn't matter anymore. Some of the really high pixel cameras are really crap, and some of the lower pixel cameras produce a very nice appealing images. So it kind of went back to not being a single number, but it used to be. And why is that? Well, because it's kind of easy for people to compare, right? It makes it lazy for comparison. So unfortunately, sometimes it happens with the scientific results as well. We say, this algorithm used 1,000 generations and this one used 500 generations. Is clearly better, right? Because it runs faster. It requires less generations to compute the same thing. But we also know there is no free lunch, right? So we also know that if you have two methods of doing something in machine learning, and that one beats that one, we also know that one will beat that one in some problems, that one is weaker. We know that's always the case. Mathematically, it can be proven, right? The question is, are the cases where this one is better actually useful, common, occurring, or are the cases which this one is better more common, right? So every sorting algorithm can be compared to any other sorting algorithm, right? So what slow sorting algorithms you know? Well, bubble sort is one of the slower ones, right? But bubble sort will be the fastest for an already sorted sequence. There is no faster algorithm for an already sorted sequence to sort the sequence than the bubble sort. It's the killer, right? It kills everything else. So, well, you have the case where this one shines really well, right? How common is that occurrence? Not that common, right? If you actually need to sort something, most of the time it needs to be sorted. So that will not be the fastest, right? But there are trade-offs. You have to take those into account. So if you say, quicksort is faster than bubble sort, not always, right? Sometimes actually bubble sort will kill quicksort. Okay, most of the time in most random arrays, quicksort is faster than bubble sort. Yeah, that's more accurate representation. So you have to be quite precise when you're comparing things, when the one which is better is actually better, and what are possible cases where it's worse, right? And benchmarks are not the greatest way of doing that, because they sort of have a kind of a blanket view of how to compare things, and for your particular case, it may not make sense. But they sort of ease the overall comparison. So even for machine learning, we have some benchmark data sets So you have the iris data set, which compares flowers and say how they sort of look like, and depending on the nature of the algorithm, sometimes you can say on this particular data set it kind of works better, right? So it gives you a little bit of information, right? So they also had in 4.2 they talked about documenting, and that's what we tell you to do as well. That when you're doing your master research, you should always take notes. Kind of keep like a short journal of what you are doing, what ideas you have, and what setup you've used, what you did. Because then when it comes to writing a thesis, it will be much of help to you. It will kind of really help you to kind of put those details in. You will run experiments which you may not use in the thesis, but you will not remember exactly how you did certain things 2 months later. So if you are planning some experiments, or if you're reading something and having some ideas, putting them down and documenting your process is very helpful. So we always stress that you should do that. Yeah, funny enough, like my supervisor was also telling me that. I was like, come on, I mean, I will remember, next month what I'm just thinking right now. So it felt a bit extra work to be putting it on paper. And I was like, come on, I will in 3 weeks I will be writing this chapter, so then I will write it. But believe me, he was right. Like 3 weeks later, you don't exactly remember what you were thinking. And you think you will, but you almost never do. So you don't need to write a proper thing. You just need to write a sentence or some words, and then everything you were thinking will come to your mind. But you have to have this kind of context. You need to write something for yourself, and it will kind of help you to recall what you need to recall. All right. I guess that's it. One small thing I also wanted to say about the paper is that in the section 3, they used so they used a couple of references. So when you're reading their paper, it's never the case that they say, oh, people in this paper did that. They never kind of do that. Like, so recall your research project plan, how you did literature review, right? You usually say, in this paper, these guys did that, or in this paper, these guys did that, right? You sort of do that as reporting on somebody else's work. In this article, they almost never do that out of context. They only do that saying, for example, something was proven in the biomedical experiments where they were some claims were falsified, and they put a reference, right? So they tell you a story, they tell you a context, and then they say, for details, look here, but they kind of put it in the context of the article itself, and that's a good way of doing a literature review. So I told you that yesterday, that you should sort of redo and rethink a little bit how you did the literature review for the project planning. And this paper is kind of a good example of that. It may be too much even, right? They almost don't tell you what these guys did in a paper, but reference to it based on the context of what they write. But so something between those two, like telling exactly what people did in a paper and kind of referring to it from the context of your work. Somewhere in that spectrum is the kind of a sweet spot. So you talk about your work, and you talk about the problems and some evidence that you need, and then you refer to somebody else's work which backs that claim, right? So they didn't do it for everything, but they did it for some of the claims they made. That's what we discussed at the beginning of the lecture, that for some claims they did have evidence, but for some they didn't, and it's kind of hard to distinguish because of the way they presented the main flow of the article. Yeah, so that was my last comment about kind of the literature review part of the article. Any other comments or questions or suggestions? All right, so we will finish here, and I will wait for your paper suggestions for your topics, and I will tidy up the table that we have and set up the Confluence page, so then we can move the discussion to your essays and to the writing the little pieces. So thank you. Bye bye.